Welcome to lecture 11 on risk management and insurance. In this lecture, we turn to the main topic of this course, which is insurance. Most material on insurance I take from the Zweifel and Eisen book. And if you're looking for a more advanced treatment, you can take Eckert, Collier, and Schlesinger. Nicholas Bernoulli stated the so-called St. Petersburg paradox. Bernoulli lived 300 years ago. He was a mathematician in Basel. And St. Petersburg is a city, the second largest city in Russia. Now let's consider a game in which a coin is thrown until it lands heads up, and suppose the payoff is 2 to the I power if this happens in the ith toss. So we throw a coin, maybe we get a head in the first throw, so we just simply get $2 because we get the head here in the first throw. Now maybe we first have a tail, and then we get the head. So we have the head for the first time in the second throw of the coin, second toss of the coin. Then we will get $4. And if it's first tail, and then the head shows up for the first time in the third throw of the coin, then we get $8. And again, the game is finished. Once you get this payout, then the game is finished. So if we get the head in the first throw, then it's $2. This happens with a chance of 0.5. If we first have a tail and then we get the head, then we will have $4. This is a chance of 0.25, because the chance of getting a tail first is 0.5, and then the chance of getting a head is also 0.5. And we can multiply those probabilities because the events are independent. And then maybe what we get is tail, and then a head. Each outcome, tail has a chance of 50%, again 0.5, again 0.5. So the chance of having tail, head is 1/8, and in that case you get 2 to the third power, you get $8 return. So what we do here is we calculate the mathematical expectation of the payout of this game. Each possible outcome is multiplied by its probability. Let's be completely clear on this. So here, maybe we get the tail in the first throw, and so we just simply get $2. The chance of it is 0.5. Maybe we get first a head. The chance of that is 0.5, and then we get the tail. The chance is also 0.5. So the chance is here 0.25, and then we will get $4 because the tail appears here in the second throw. You see the tail appears here in the second throw, and so we get here the $4. But another, maybe we have head, and then the tail shows up in the third toss of the coin. In that case, we get 2 to the 3 power. That's a payoff of the game. We will get $8. And then you see here something very interesting. You see the mathematical expectation of this game is actually infinite. The mathematical expectation of the payoff is infinite. If we multiply each outcome with its probability, we get here 1 + 1 + 1 + 1, we get infinite. It approaches infinity. You see the 2 cancels out against the 2. Here's a 4 cancels out against the 4. So 8 against the 8. So it's just 1 plus 1 plus 1. And we can throw the coin an infinite number of times, possibly. So the mathematical expectation of the game is infinite. And that's a paradox. You see, what would you be willing to pay for this game? Think about it. Yeah, probably not much. You see, so that you get $8, the chance is 1/8. That is still quite likely to happen. But then to the $16, so the chance is only 1/16. So the chance falls here rapidly. So it's quite unlikely that you will be willing to pay more than about $20 or $30 for this game. But there is an expected payout of the game is infinite. So it's billions, it's even more than billions of dollars. That's expected wealth. Now W here stands for wealth. So although the expected payoff of this game in dollar terms is infinite, people probably, few people would be willing to pay much more, maybe than $10 or $20. So that's the St. Petersburg paradox. Now, Gabriel Cramer, he lived also in Switzerland 300 years ago. He lived in Geneva, and he suggested what matters for people is not the dollar values of the payoffs, but their utility. And Daniel Bernoulli, he suggested that the utility function is logarithmic. Now, a logarithmic utility function implies that the utility increases at a decreasing rate. You know the utility function is upward sloping, but it gets flatter and flatter. And so the large payoffs that may occur with low probabilities, they do not add much to the expected utility of the game. That's because the utility function is getting flatter and flatter. Now, Daniel Bernoulli, by the way, he was a brother of Nicolas Bernoulli. They were both mathematicians and they contributed to probability theory. Also, their father actually was a mathematician. Now, there was interest in probability theory 300 years ago because the aristocrats, they played their fortunes away in the casinos of Europe. Now, also St. Petersburg had casinos, and so they went to those casinos, the rich people, and they played. And so that's really was a motivation to develop utility theory, to develop probability theory. Now let's now calculate the expected utility of the game. So we have still the payouts here. Xi, that's a payout of the game, but we take now the utility of it. And each utility is multiplied by the probability of such a payout. So we calculate now, here's a mathematical expectation of the expected utility. Now the payout is still 2 to the I power. That's just a game, but now it's not that dollar value here which matters, but it's a logarithm of it. So we have this utility function. And the probability is 1 divided by 2 to the I power of a certain payout here. You see, here it's 1 divide 2 to the 1 power, 2 to the 2 power, 2 to the 3 power. So the probabilities here follow also the powers. So each utility that you receive, that you may receive here, you multiply with the probability. And then you have the expected utility of the game. Now let's assume, let's use the logarithmic law. So the power comes down. I'm getting I times ln2. So just use the logarithmic law here. And ln2 then is a constant. So I'm allowed to factor it out from the summation. So I then naturally shows up here. And this sum here is a mathematical series which converges to 2. That can be shown quite easily. So the sum approaches 2 here, and then we have ln2. So the expected utility of the game is finite. It's finite, it's only 1.39. So the expected dollar value of the game is infinite, but nobody is willing to pay much for it, so it's a paradox. And the expected utility of the game is finite. So it seems that you're taking a utility function, a logarithmic utility function, really resolves this St. Petersburg paradox. People do not want to pay very much for this game because the expected utility is not very high. Now, some comments here. Truly, taking a logarithmic utility function does not solve the St. Petersburg paradox in all situations. We can construct a new game with a new payout. Let's assume the payout of the game is not 2 to the I power, but e to the 2 to the I power. So if the head shows up for the first time after throw I, then the player will get e to the 2 to the I power. Now, so that's a new payout. And if you take the natural logarithm of that, you get just 2 to the I power. So you are back now with the old game, 2 to the I power, which has an infinite expected value. So here, so logarithm will approach infinity of the game. And so again, okay, we are back with the St. Petersburg paradox. So the expected utility of the game now becomes infinite if we work with this payoff of the game. It can be shown as long as the utility function has no upper bound, payoffs can be set in a way that the expected utility of the game is infinite. So logarithmic function does not have an upper bound. It's upward sloping, it gets flatter and flatter, but it never approaches a fixed value. It's just getting flatter and flatter, but never approaches some fixed bound. So maybe let's draw that. So if you have the utility function, it is upward sloping. It's getting flatter and flatter. So but it never approaches some kind of fixed value. It's always a little bit upward sloping. Now a function with an upper bound will approach some fixed value here, which is the upper bound. So logarithmic function doesn't do that, and that's why you can construct now new games where even using a logarithmic utility, you will get now infinite expected value. Another assumption that is important is that the party offering the game, maybe the casino, will not run out of money. And it will never run out of money. So it has infinite wealth. If its wealth is finite, then there's a slight chance that it may run out of money. And this then really reduces, again, the expected utility of the game actually quite a lot. Okay, that's 2 comments. So we have here to expect, even with those limitations in those comments, people then use expected utility to explain behavior in uncertain situations. So we have the expected utility hypothesis. It states that people assign utility values to uncertain payoffs, and they choose that game or that action which produces the highest expected utility, and not that action or game with the highest expected monetary value. So we have here uncertain payoffs, uncertain situations, and people will choose that action which produces the highest expected utility, and it's not the highest expected monetary value is not important. Now, von Neumann and Morgenstern wrote down, they provide the necessary and sufficient axioms for such a utility function to exist. That's usually discussed in intermediate microeconomics classes, but we don't do it here. You can look it up in this textbook. It's quite good. Von Neumann was a famous mathematician. You may know him. He was active in the 1930s, 40s. He also was important for the development of the computer. But he died quite young, in his around 60 years old. Now let's discuss here risk aversion. Let's consider a utility function, a utility out of wealth, which is increasing on concave in wealth. So it has a positive first derivative and a negative second derivative. So the utility function is concave. And an agent or person with a concave utility function is risk averse, because a loss of H dollars weighs more than the gain of the same size. That's what I show here in this graph. So we have here wealth on the lower axis. We have the utility out of wealth on the upper axis. Let's assume the utility function exists. So we have those axioms of Neumann-Morgenstern. Now here we have initial wealth that's just W0. And let's now have, with a chance of 50%, wealth is increased. So this will increase utility by so much here, by this red line. And with a chance with 50%, let's assume that wealth falls. And this will reduce utility by the red line here. So with 50-50 chance, either utility will increase or will fall. And the person, the insurance buyer or the person will not like this, because here this increase in utility is less than this falling utility here. That's because we have here a concave curve. So here, this increase is smaller than this fall. So a loss of $H weighs more heavily than a gain of the same size. A loss of $H here reduces utility more than the gain of $H. That means that the person is risk averse. So the figure may again represent a game of coin flipping, in which the player receives $H or loses $H. So the chance is 50-50. Now that it's a different game from the one in the St. Petersburg paradox. Much easier game, much more straightforward game. It's just flipping a coin, and you receive money, $H, when there is a head, and you lose $H when there is a tail. So with 50% chance, you make a gain. With 50% chance, you make this loss. But the loss here is bigger in utility terms than here the gain in utility terms. The game is fair. You see, it's the expected payoff is 0. It's 50-50% chance. So the expected wealth equals initial wealth. So the expected wealth will be equal to initial wealth. It's a 50% chance of earning $H or getting $H, 50% chance of losing $H. So it's a fair game. Now, according to the expected utility hypothesis, an agent compares now the expected utility of playing the game with the expected utility of not taking part in the game. So the expected utility of the game is just 0.5 times the utility of this increased wealth, of this reduced wealth, of having a loss, plus 0.5 times here having the increased wealth. So U's are here again functional operators. So that stands for the utility function. And for obvious reasons, I'm taking here a small u. I don't taking a small f for the function. Okay, here I deal with a utility function. It's naturally arbitrary what kind of letters that you're using for functional operators. So here we have the expected utility of the game. Either the person has higher wealth or the person has lower wealth. This happens with each happens with a chance of 50%. So 0.5 times the utility out of the lower wealth plus 0.5 times the utility out of higher wealth. That gives me the expected utility of the game. That's just how you calculate mathematical expectations. You multiply the outcome with its probability. Now here, the outcome where the player wins multiplied with its probability. And the outcomes are now measured here in utility terms. Now the expected utility of not taking part in the game is just simple equal to the utility of initial wealth. The expected utility of not taking part in the game is just the utility of initial wealth. You see, it's a fair game. So if you take the expectation here, it just calculate here the expectation of the utility of initial wealth. Initial wealth is a constant, so utility is also a constant. And if you take the expectation of a constant, you just get a constant. That's something you know from statistics classes. So if you don't take part in the game, you just keep your initial wealth, You have this utility out of the initial wealth, and you take the expectation of that, but the initial wealth is constant, so utility is constant, and so the expectation actually does not matter. Because the expectation of a constant is just the constant itself. So that's something you learn in statistics classes. So the expectation of a constant A is just equal A. Now, a risk-averse person does not prefers not to take part in a fair game. Even if the game is fair, a risk-averse person will not take part in it. So let's calculate the utility. We have them now here. The utility of not taking part in the game, the expected utility, is just the utility of initial wealth. So that's equal to expected utility. The expected utility of the game we have from up here. So both are just expected utilities. We put those things, and the expected utility of not taking part in the game is bigger than the expected utility of playing the game. So a risk-averse person will not play. And here you see why. So in this graph, I have again wealth on the lower axis, and the utility here on the upper axis, and I have here again the utility function. Now, if the person takes part in the game, then the wealth is with 50% chance higher than initial wealth, or so with 50% chance the person loses and wealth will be reduced. So with 50% chance, utility will be here, and with 50% chance, utility will be up here. And because it's 50-50, the expected utility is just in the middle. Which means it's also in the middle along this straight line. And if the person does not play the game, then the person just keeps initial wealth. Okay, just nothing happens, and the expectation of it, expected utility of it, is just the expected utility out of initial wealth because it's a constant, and we are here up at point A. So expected utility of not playing the game exceeds the expected utility of playing the game. And according to the expected utility hypothesis, then the person will not play the game. Because the person just compares those two expected utilities. Okay, that's pretty neat. So point A shows the utility or expected utility of not playing, and point B is the expected utility of playing. Point B, you get it because with 50% chance we are either here, and with 50% chance we are up here. So the expected utility is just in the middle. So that's the expected utility of playing the game. And if we don't play, then just we have certain wealth. And this certain wealth, the expected utility out of certain wealth is certain wealth because it's a constant. So as expectation drops out. So the expected utility of not playing is bigger than the expected utility of playing. And according to the expected utility hypothesis, then the person will not play. So the game is fair, and the person prefers not to play, and such a person we call a risk-averse person. The person does not like the risk. The person prefers a certain situation. Now, a risk-neutral person will be indifferent between playing and not playing. So here I have a risk-neutral person. Here's a utility function, simply straight line. So here's the expected utility of the game becomes equal to the expected utility of not playing the game. And the person does not care about the risk. And so the person may play or may not play. We cannot explain it. It will be just by chance. The person is indifferent. You see, if this curve becomes flatter and flatter, then okay, this distance here disappears, and point A will match point B, and this will also match down here. And so the person, there is no longer a difference between the expected utility of the game and of the utility of not playing, and so the person is risk neutral. A person may be even a risk seeker. Now, if the utility function is convex, then the expected utility of the game is larger than not playing. And so that the person will then really go to the casino and play. Okay, that person just likes okay, the risk. Now, most people are probably risk averse. People will differ. Maybe some people are strongly risk averse, since they have a strongly concave utility function here. Other people are less risk averse, then maybe their utility function is flatter. So then A is closer to B. But in most cases, for most people, the utility function will be concave. So the utility function here shows the tastes of people. It shows the preferences of people. How much do they like risk, or how much do they hate risk? And this will be different from person to person. So different people will have different utility functions. But in most cases, it will be concave. Maybe a few people are risk neutral, and even less people are risk seekers. So that's possible, but okay, that's not the average person. So here today we introduced something very important. We introduced the expected utility theory of behavior toward risk. The starting point was the St. Petersburg paradox. Now, this expected utility theory of risk does not completely explain the paradox, but still people use this expected utility theory of behavior toward risk. It's really the basic model that we use in finance classes when we discuss the behavior of people in financial markets. So it's a very important model. So that's the lecture for today. Thank you.